Good morning, students. Today we are going to see that applications of complex integration and Laplace transform in embedded systems. So why we need complex integrals and Laplace transform in practical systems like embedded system. Before that, I want to explain that what is embedded system. So embedded system is nothing but it's like it was combination of software and hardware. So for example, if you are having a TV remote or AC remote, it has a microprocessor inside that remote. So it controls that sensors in that AC. So now, we have a hardware, but also we have a software. So that software has a particular task. So it was not having a enlarged task like our computer. So end of the day, embedded systems like our computer, but it has a specified tasks. So that is the think of embedded system for now. So before entering to the particular topic, I want to explain that what is the embedded system. Now I just completed that. So while we are entering into that embedded system, I just want to recollecting that complex integral concepts. So complex integral is nothing but it was a complex integration is an essential for understanding the signal behavior in embedded system. So we need a complex integral in embedded system to understand the signal behaviors. So likewise, we just mathematically modeling that signals in mathematical equations. So after that, we just doing some transformations and calculations. So to understand that signal behavior, so that's the concept of here. So and then embedded systems are nothing but it involves signal processing and then filter design and control systems where that complex integrals plays a significant role. So nothing but if we are having a embedded system. So now we are receiving signals from our remote. So it was received by our sensors in our embedded system, whatever AC or TV. So there it has a filter design there. So whatever the signal arrived there, it was filtering it. So because the noises will disturb that, so that's why we need a filter design there. After that, there will be a control system. That control system is nothing but it was giving some commands. It was receiving a command and it was put it as a bounded one. So then only we can receive a finest result from that embedded system. So that is the case. So for there we need this complex integration particularly. So that is the case. So while we are designing a filter, we need this. While we are giving a controlled command for the control system, we need this complex integration. So what are the key theorems used in this embedded systems means the Cauchy's integral theorem, Cauchy's integral formula, Cauchy's residual theorem, but also the Laplace transform plays an important role in embedded system. So that's what the things I just want to tell you here. So in this session, I was interested to explain both theory things, but also that practical applications of complex integral in the embedded systems. So now, what does Cauchy's integral theorem tells us means, if suppose we are having a function, that function is an analytical function. Analytical means nothing but if a function is differentiable at a point, but not that particular point, it was also differentiable at the neighborhood of the whole points. So then it is known as analytical function in terms of complex functions. So now we are having a complex integral over here. So in the complex integrals, you are having a closed curve here. So while we are trying to integrate a function f of z under this closed curve, if suppose my f of z is analytical on this closed curve, then I conclude that my integral value is equal to 0. That is the case. So that is what Cauchy's integral theorem tells us. So here the Cauchy's integral theorem it was crucial because it simplifies the many integrals in embedded system. Because while we are having a embedded systems, So we have a mathematical function. That function is analytical, means we don't need to integrate on that integrate that complex functions. So because it was already we know that from the Cauchy's integral theorem it was equal to 0. So that is the main role of the Cauchy's integral theorem there. So now we have an example for that. So while we are having a Cauchy's integral theorem, so we can evaluating the total response of embedded system filter. So the embedded system filter response is that. So to evaluating that, we are using this Cauchy's integral theorem. By using that Cauchy's integral theorem, we make that complex integration very simply. It was equal to 0. So that was the case. So now we are having a Cauchy's integral formula is there. So while we are having a Cauchy's integral formula, we don't bother about the function is analytical or not. So it was not required that. So while we are having a function in the form of it was in the form of fractional. So we can't check that analytical set easily. So that is make the things more complex. So in that case, so we are using this Cauchy's integral formula. So Cauchy's integral formula helps us to evaluating the complex integration in the case of we can't confirming that our f of z is analytical or not. So we don't have an option to confirming that. In that case, we require this complex integration formula. So this Cauchy's integration formula is tells us nothing but while we are having a closed curve here, right? So in the closed curve, we are evaluating this integral. So I have an integrand f of z divided by z minus z naught into dz. So this was equal to nothing but f of z naught. That means initial point. So at the initial point, we are checking that our function value. So that was equal to 1 by 2 pi I integral over the closed integral f of z divided by z minus z naught into dz. So this is what Cauchy's integral formula tells us. So while we are applying this, so we have only this part. To evaluating this part, we just send it to this side. So that is what the main idea behind this. What is this z naught meant for means that z naught is nothing but singularity of this function, singularity of this integrand. So singularity means while we are substituting that z naught here, it makes this function indefinite or infinity. So that in that case, that particular point is known as singular points, singularity points, right? So on while we are having the singularity point, just we evaluate the numerator by the singular point and multiply it by 2 pi I. That was equal to this integral value. So this is what Cauchy's integral theorem basically in terms of mathematics. So what is the role of it in the embedded system? So while we are having an embedded system, it allows to calculating the system respond at specific frequency. So on the particular frequency, we can evaluate our response by using this Cauchy's integral theorem. So why we need this means while we are having a inverse Laplace theorem. So by using that inverse Laplace theorem, we are having some calculation. So after that, we need this integral requirements there. So that is the role of it. So while we are calculating the again it was helps us to calculating the filter response of the embedded system. So that is the thing here. So the significant role of it is while we are having a real-time behavior. So we need a computation of frequency of the domain response. So it was very complex one. So while we having a practical system, it's not very easy as our normal mathematical problems. So it was more complex. So on that time we need this simplified formula forms. So that is why we are using this Cauchy's integral formula there. So here I have concepts of poles and zeros. So poles and zeros are nothing but poles and zeros of a system transforms a function defined into frequency response and stability. So the poles is nothing but the value of s where the transform function goes to infinity. If my transform function, I have a transform function, the transform function is tends to infinity on that point s means that point is known as poles. Already we know that singularity points. So that where that singularity point is there, so that is all that is what known as poles. So zeros is nothing but it makes our function as equal to g. That's the concept. So stability of the system is nothing but a system is stable if all poles have a negative real parts. If my pole is a complex number, it has a negative real part, then my system is stable. That is stability concept. While we are converting our embedded systems into the complex function, so this is what that stability definition there. So in control system, the poles indicates the system natural frequency and damping factor. So that is what the pole indicates there. So as a practical one. So this is what the Cauchy's residual theorem tells us. Now we are having the concept of poles. Wherever the poles are there, so we can find a residual for that particular poles. So for each pole we have a residual. Here the formula is nothing but the integral over C f of z dz is equal to 2 pi I summation of the residual of f and at particular that poles. So what is the difference between the previous theorem and this theorem? In the previous theorem we consider that numerator separately, denominator separately. Here there is no need of it. We just consider the whole function, whole f of z as a function, right? So here itself we consider the whole function as taken for a consideration. So it was very easy compared to the previous one. If we are having more poles for a function, more factors in the denominator, so it makes complex there for the integral formula. But on that case, you can use this Cauchy's integral theorem. So that is the particular use of this Cauchy's integral theorem. So the Cauchy's integral theorem is more reliable and more robust one. So what is the use of the Cauchy's residual theorem? What is residual first of all? The residual of a function are nothing but it's a coefficient of a Lorentz series of a function around the singularities. So while we are converting a function into a Lorentz series, the coefficient of the Lorentz series function is around that singularity is known as residual. So used in the embedded system, the residual theorem is essential when evaluating the inverse Laplace transforms of a system's transform function. So while we are having a transform function of a embedded system, so we are taking that inverse Laplace transform for that. So on that case, we need the Cauchy's residual theorem. So for example, computing the inverse Laplace transform of a transform function to determine the time domain response of a filter, on that case we have some integral terms inside that inverse Laplace transforms. So to evaluate that integrals, we need this. So that's a case. So here I have an example of calculating the residual calculation of an inverse Laplace transform. So I have a function. This is what my transform function. So transform function of an embedded system filter response. So now I am just taking an inverse Laplace transform of this one. So after taking that inverse Laplace transform of this function, I am just having to taking that, I am just factorizing this one, and then I have poles like this. After I have a poles, I just finding the residual for this one. So by using the residue on the inverse Laplace transform, we can compute this one. So the stability and frequency response is nothing but the frequency response of the system depends on the location of the poles and zeros. So where the poles, where zeros are there, the stability depends on that. So unlike we checking the stability over the whole system, we checking the stability of the poles, the stability of the system at the poles, stability of the system at the zeros is NOC. So that is the concept. So and then that for a stable system, the pole should be lies on the left half of the complex plane. If we are having a we are marking the points on the complex plane, if my poles on the left side, why I require that left side means I already mentioned that the real part of the pole should be negative. So if it is negative means while we are marking that point in the complex plane, So that was purely belongs to the left side of the plate. So that is the concept here. So here the application of this one is nothing but in a signal processing, the poles near the imaginary axis leads to the acceleratory behavior. That means it may be a stability, it may be stable or unstable. Sometimes it was stable, sometimes it was unstable. So likewise it was both. So that is the concept here. So for example, if we are having a low pass filter, so low pass filter is a filter. It was used in the electronic system. So while we are going to the that circuit analysis and other system designing concepts, so you will learn about this low pass filter. So particularly the low pass filters are used in the control systems. So while we are having a low pass filters has a pole at a negative real part, so leads to attenuation of high frequency. So that is the concept here. So the applications here I am just tell you in previous I was planning to deliver that theory part, but also the application part. So here some of the application is given over here. So that first application is digital signal processing. In digital signal processing, the complex integration is used to evaluate the system frequency response, but also the filter designing. So while we are having a filter designing, we have a transfer function of a filters are analyzed using the complex integration. So while we are having a transform function of a filter, so we are having a transform function. After that, we need to convert it into the time domain. So converting it into the time domain, we need to take an inverse transformation there, right? So while we are taking the inverse transformation, we need this complex integration. So that is the case. So for example, an audio system filter where high frequency noise is removed by using the low pass filter. So the low pass filter is used there. So mathematical application here is nothing but the inverse Laplace transform are computing using the residual method to determine the time domain response. That is what I am explaining now. So the application, that low pass filter application, I am just given some calculations here. So some equations, mathematical modeling of that particular system. So here I said some filter specification. The filter specification is nothing that it was specified engineering things. So we have a cutoff frequency here, and then order here. Order means in our mathematics the order of the pole. So the order of the pole is around 4. So we are having a transform function here. So this is our transform function. After that, taking in this particularly we have a function pk. We just defined that function pk. It was purely engineering things. So while we are having a transform function, this is what our transform function. The remaining things are specifying what else belongs to this one. So here itself, I am just using that Butterworth filter poles. So by using that MATLAB, I am just drawing this one. So this is specifically just get it from that MATLAB. So MATLAB calculation. So by using the filter Butterworth filter poles by order 4, I'm just drawing this. So here you clearly see that the pole is here. That belongs to left hand side. Therefore, our system is stable. So that's a concept. We are by drawing this, I can get this data. So that is what the computation purpose here. So if it is not belongs to this stability region, if it is belongs to this one, then it was unstable. If it is belongs to the middle point, then it was auxiliary. It was gives some auxiliary responses. The application 2 is stability analysis in the control system. So while we are having a control system, so stability of the system is evaluated by analyzing the poles of its transform function. If any poles has a positive real part, the system is unstable. Already I mentioned that if the pole has a negative response, a negative real part, then it was stable. Otherwise, it was unstable, obviously. So that was given you. Here, the application here is in the control system, particularly in robotics, where the feedback loops must maintain the system stability. So that means while we are having a robots here, so we we need some feedbacks. That means whatever the actions of the robots, we need to monitor it and receive feedbacks from it. That means we assign a task to it, it was done the task. After done the task, we need feedback of it while we are having a class. So in after my class is completed, so I'm just taking a feedback from you. Why? Because while I'm having a feedback, I just reboot it and just make some changes in my class. So that is very helpful to you. So that is what applicable for the control systems also. So that is what here. So the using the complex integration to calculate the system stability in the robotic arms or autonomous vehicles. Not only the robotic arms but also for the autonomous vehicles. That means like our Tesla vehicle is there now. So that was an automatic vehicle. So while using that automatic vehicles, so we need a feedbacks from the system. So that feedbacks is again given to this control system. So the control system is little bit modified itself. Then it was running towards it. So that is the case here. So the mathematical application here is nothing but the poles zero analysis provided information on the damping and the natural frequency crucial of turning the control system. So the pole and zero analysis is very important for this one. So that is the case here. Okay. The control systems stability analysis is given over here. I'm just using that PID. I'm just taking a, for example, I'm just using that PID control here. So PID control is nothing but the proportion, integration, and derivative control. That is what the controller PID meant for. So now I'm just setting that system assignment here. So that is, I'm just taken a open loop transfer function over here, and then I just have a PID controller that was defined over here. So now I'm just having a closed loop poles. So I'm just defining a closed loop poles here. So while I'm just evaluating this closed loop poles, I can confirm my stability over there. So for that I need this control gains, this K values. This control gains preserve that stability of the system. So what is this role of the control gains means? It was in the control system. So the control gains are tells us how working that control designs be done here. So here the case study given over here that already mentioned that in robotics it was very applicable, right? So I'm taken a control system of robotics. So I am just taken a problem here. The robotic arms needs to maintain a stability while performing a task. So that is what my problem here. So if it is not having a control stability over there, means the robotic arm maybe make some mistakes. If suppose I'm just given a major task, it may, if it is done a mistake, means it will be a crucial problem there, right? So so we need a stability of the robotic arms there. So for that I have a solution by using the complex integration to analyze the transfer function of the robotic system. So the feedback by using the feedback loop, so it was resolved. So that is what this is what I am taking a problem here. So while we are having a design thinking things, we need a problem, we need a solution. I have a problem, I have a solution here. For that solution, I need to calculate the poles and zeros there, so determine the location of the poles and zeros to ensuring the system's stability and performance optimality. So that was that methodology over here. So for that I am just going to use the residual theorem here, used to evaluate the system response in the frequency domain, leading to better control system designing. So that was the system set, the problem setting here. So here I am just having a robotic arm control system. So it was nothing but the reference signal given to the system, and then it was went to the PID controller. After that it was went to that filter design. So after that it was having the actuator, so that actuator functioning it. So after that it will give you some feedback. So that feedback is again feeded to our controller. That is the case over here. So this is that thing that designing challenge is nothing but to prevent the actually oscillations while tracking the high frequency trackers. So while we are having a high frequency trackers, that was really difficult to prevent the oscillations. So that is the difficulty over there. That this is the setup of the robotic arms. So the thing is, the calculations done here is nothing but we have a transform function. After that, we are using our inverse Laplace transform. While we are using the inverse Laplace transform, we just applying the complex integration. But the application is very big. That is the things. So here I am just given the step response of the system and the frequency response of the system, and this is purely controlled systems. So this is not a big deal here. So the big deal is here, all those things are done by using the mathematical calculations. That is the thing. So here I am just using that inverse Laplace transform for the filter designing. So we are seeing that inverse Laplace transform in the unit 3. So while we are having a Laplace transform, we also have a inverse Laplace transform. So Laplace transform is used to convert a transfer function from the frequency domain back to the time domain. So while we are having a Laplace transform, it converts the time domain function to the transform function, frequency domain. So after I done my analysis, now I am just refill it. So again I just convert it from the frequency domain to the time domain. That is the case. So that is what I think here. So I am just applying the residual theorem here, and application here is the embedded system and filter designing. The inverse Laplace transform determines how the filter responds over the time. So after a long time, how the filter response will be. So we need to know that, right? So for that we need this filter design over here. So I'm just given an example for that. That is nothing but audio filter designing. So the audio filter designing, where we taking a problem, that is nothing but a design a filter to attenuate high frequency noise as an audio signal. So we have a high frequency noise there. So we just need to convert it into the audio signals. So for that we need a solution. So that solution is given by computing the inverse Laplace transform of the filter transform function to determine its time domain behavior. So by transforming a transfer function into the time domain function, we can predict that or we can ensure that the time domain response. That is the case. So here the mathematical application is the filter domain. A time domain response is crucially for implementing the real-time audio processing in the embedded system. That is the case. So here the case study is given over here, that this is what the transformation function. And pole zero placement here is nothing but the normalizing the pole. So after normalizing the pole, we just ensuring that the pole belongs to the stability region. If it is, means we can tells us our system is stable. So after that, the implementation of it is nothing but we need the bilinear transformation here. What we learned in the 4th unit, the bilinear transformation is nothing but we already have some points. That point is converted to the another point. So now we need a transformation function there. So by using the bilinear transformation, we can have that transformation function here. Bilinear means nothing but the above one is linear, the below one is also linear. The combining of both is known as the bilinear transformation. Then we have a second order section SOS. This is the transfer function here. So we using the fixed point optimization technique over here. So this is the thing we learned here. The conclusion of this one is nothing but the complex integration and the Laplace transformation, inverse Laplace transformation is a powerful tool in the embedded system. While we using the embedded system to calculating the various things, we need this. So that's what the thing concluded from this one. So moreover, the key techniques is we are using is residual theorem and the Cauchy's integral formula. So that plays a vital role there. So in real life, the audio signals processing system, the robotic arm systems, and many other systems are using this one. So while we learning the mathematical things, we need to know the application of it. So that is what the conclusion of this one. So hope you enjoyed the lecture. Thank you all.